compared to atmosphere. Okay. So this is the concept of the ground-based GPS meteorology. Because the thickness of the atmosphere is dependent on the elevation angle, we can estimate the zenith total delay as an independent parameter together with the station coordinates. And this total delay is composed of hydrostatic delay, which can be calculated from the surface pressure. So you can isolate the water vapor. And this is very useful information for weather forecast. And Japan is one of the few countries actually using the GPS-derived water vapor information in the actual weather forecast mesoscale model since 2 years ago. So by incorporating the GPS information, there's a significant improvement in the forecast accuracy. And I don't talk much about meteorological stuff, but something with longer time span from GPS meteorology to climatology. So this is the 15 days in summer at this station, the northernmost GPS point. And if it is 1 year, you can see the seasonal change. In summer, there are more water vapor because it is warmer. And now it is 5 years. And if it is 13 years, you are starting to see something climatological. For example, this is a station in central Tokyo and one in southern Japan. And I model the time scale, time series with seasonal plus cubic polynomial. And these smooth curves are those without a seasonal change. And I try to compress this. Now you can see something. So this degree 3 change, this is possibly reflecting decadal climate change known as Pacific decadal oscillation. So this is one of the climate signal in GeoNet water vapor. And also you can see the ENSO signatures. El Nino brings a mild winter in southern Japan and opposite in La Nina winters. And this is the time series of the SSD of the Peru coast. So this is a kind of ENSO index. So I would take out 2 winters. This is La Nina winter, and second, this is El Nino winter. And compare the residual from the standard seasonal curve. So you can see that this winter is colder than this winter. And it is mainly influencing the southern half of Japan. And even we can see the solid Earth signal in GPS meteorology data. For example, this is geoid. And there's a geoid low along the Japan coast and making the slope of the rather steep slope of geoid relative to the reference ellipsoid. Especially it is the case in the Kanto district. And atmosphere is stratified in parallel with geoid, of course, but we calculate the elevation angle relative to reference ellipsoid. So this causes a kind of apparent atmospheric delay gradient. And this is expected gradient. It is not more than 0.5 millimeter, but this is large enough for us to see. For example, this is a time averaged gradient. This is supposed to be tending south, but there is some clockwise deflection in the Kanto area. So I think this is coming from geoid.